the ICCAC's webinar series, and today we have Friedrich Kaufmann from the German Heart Center in Berlin. He's one of their senior coordinators, and he's going to talk about the HeartMate 3. So with that, just some businessy stuff to go along. I'm going to mute everybody's microphones so Friedrich has the stage. If you have a question that can't wait till the end, there is a little guy with his hand up on the bottom of your box, so you just click on that and it'll alert me that you have a question. Otherwise, at the end, we'll entertain all questions. And we're just hoping this all works. Just know that we have been messing with this for 2 days, and it's going to work, or we'll end up recording it so you can watch it later. So with that, I'm going to hand things over to Friedrich and mute everybody's microphones, and there you are, sir.
Okay. Hello to everyone. This is a presentation coming from my presentation at the ISAO in Warsaw earlier this year. It's admittedly a little bit technical, so I hope you will be fine with that. Theoretic HeartMate 3, or SJM as it is nowadays, is, from my perspective, a black box. What is a black box? It's a device or a system without any knowledge of its internal workings. Of course, we know a lot about the HeartMate 3, but we don't really have insight into the system compared to other systems. Fortunately, the HeartMate 3 is a system which is going like the famous Volkswagen Beetle, and there are minimal handling requirements, though there also is minimal information, as I already told, about the system performance. And I would like to illuminate a little bit this black box with this presentation. So to start with the features of the HeartMate 3, we have the first system with integrated electronics. That means there are log file storage and parameter settings in the pump itself. That means for the patient, if there is an issue with the pocket controller, anyone can be used for exchange because all the necessary information is stored inside the pump. The video is working. I hope you can see that. Rotor spinning, and now zooming out, you see there's only a battery attached to the pump itself. Now, the second big advantage is we have active magnetic levitation. That means no contact, no friction, and thus no wear. There's the so-called wide gaps enabled by the active magnetic levitation between rotor and housing. That means a high secondary flow, a better washout, and thus low risk of pump thrombosis. But I would say it's a low risk, but it's not a no risk. We will see later. Third issue is the artificial pulse. Reduction of rotary speed and increasing rotary speed, forming a flow pulse, with the idea of potentially reducing GI bleedings, aortic valve insufficiency, and thrombus formation. The time will tell if this is working. The problem is the effect is about 20 millimeter mercury maximum, and this is highly dependent on left ventricular contractibility, as you can see on the right side. If you have no contractibility, the artificial pulse can be recognized in the artificial blood pressure curve. If you have some contractions of the LV, looking to the down picture, you see no or almost no reaction from the artificial pulse. So it's a little bit questionable with most of the patients if there is an effect of this artificial pulse, hemodynamically effect. So now the negative issues. It's mostly about system diagnosis. For the diagnostic features, we need the pump and the PC controller and the clinical monitor. Still, as with the HeartMate 2, we have only 250 data sets. That means if we have a persisting alarm situation like PI events, only a few hours of follow-up will be in the internal memory. There are also log files, also with only 256 data sets. That means if we put them on the lowest sampling rate of 24 hours, one data set per day, we could cover 9 months, but of course this information is not very usable. If we have a high rate comparable to the HVAC from hardware, we will cover only 2.5 days with the 256 data sets. Also, on the clinical monitor, there's only displayed a small choice of stored parameters. On the right side, you see all these parameters which are stored internally, but only the red-marked items are shown on the monitor. E.g., there is no information about the magnetic levitation performance, which can be very interesting, I would like to say. Also, there is some kind of discrepancy with the alarm entries. As you can see from this picture, there are 226 events recorded and stored internally, but there are only 4 events displayed on the clinical monitor. This is because the alarm situation, like a low flow situation, has to persist more than 10 seconds in order to be displayed on the monitor. And this can be questioned if it's okay or if it's a good solution. Well, this addresses almost the same. This addresses the same. We experienced, or we took knowledge of this problem when we have seen some low flow alarms, right, on the pump, but no entry in the records. So this was a little bit astonishing for us. Now, for the daily use of the hardware tree, how do we verify the correct speed setting? Because speed setting is almost the only parameter we can change with the device. A little bit theory in the beginning. If the pump is working with one rotational speed on a so-called HQ curve. So if we have a varying pressure head of the pump, we get varying pump flow, as you all know. We have the contractions of the left ventricle in this example of about 20 millimeter mercury, and the result of the pump flow will be between pulsating pump flow between 2 and 6 liters per minute. We don't have curves on the, on the heart-made systems, like with other devices, as you can see on the right side, in order to check if the speed is correctly set. Look at these 2 images on the right side. We have normal pulsatility in the above picture. In the lower picture, we have suction events. So the pulsatility tells us a lot. With the heart-made systems, we have the flow pulsatility, or PI index, as a surrogate for the left ventricular unloading. That means a low PI, low pulsatility, would mean a good unloading. If we have a high PI, high pulsatility, there would be strong contractions or some suction, causing also a high PI. And the PI events are recorded in the device if we have changes in pulsatility of about 45% in a 6-second interval. It's not recording if we have a low or high pulsatility, but only if we have some change in the pulsatility. So we cannot see the flow curves. In order to establish a correct setting of the speed, we can only see the PI. That means we have no real plausibility check for suction episodes. We have no ad hoc evaluation based on technical monitoring. And we have only a very limited evaluation of past situations because of the limited or restricted memory capacity of the controller. Now, let's look to some real data from patients, the PI as an indicator for suction, comparable to the HeartMate 2. On the left side, we have low speed, a very high PI, low flow, the blue lines, dotted lines, and we increase rotational speed. On the right side, we have a higher flow, a low PI, but we also have a lot of PI events. That leads to the conclusion that the speed is too high on the right side. The low PI will indicate a very good unloading of the left ventricle and therefore the risk of suction. The problem with the PI, especially with the HeartMate 3, is that it's not very indicative, especially in the mid-range. Look to these pictures. Above, we see a real suction situation, as you can see on the arterial blood pressure line. The calculation of the PI is 3.4. The second one, we have almost no pulsatility in the arterial blood pressure. That means you have very good unloading, no contractions. The PI is 4.0, almost the same as 3.4. In the next picture, we see good contractions of the left ventricle. Again, PI is 3.4 with opening of the aortic valve. And in the bottom picture, we have a very good contraction. It's looking like a normal arterial blood pressure curve, very good contractions. The PI reading is 3.7. That means it doesn't tell us anything in this mid-range. We cannot determine from the PI, is it a suction situation or is it very good contractions of the left ventricle, and thus we don't know about the filling state of the left ventricle. Now, we experience some erratic behavior of the PI event detection. Look at this picture. We have low PI or okay flow in the range of 6 liters per minute. Now, there's a drop of the flow, increase of the PI index, and there's the PI event detection, which causes a drop of the flow. Indicating would be a high PI, good contractions, and not completely unloaded of the left ventricle. So this is really contradictory to what we have learned before, or what we could derive from our deductive thinking about the system. Of course, it's difficult to interpret this picture because we don't know if the high PI and low flow causes a PI event, or if there's a wrongly detected PI event, reducing rotational speed and thus decreasing the unloading, causing on the other way a high PI, because not unloaded left ventricle would have contractions. So the PI itself is not really telling. Possible cause of this erratic behavior, especially with the heart rate 3, is the curved HQ curve of the device. If we have a low flow situation with high pressure head, we have in this picture contractions of the left ventricle causing a pressure head variation of 20 millimeter mercury. We will have a very high flow pulsatility. If we have in the high flow region the same contractibility of the left ventricle, it will cause, because of the much steeper HQ curve, only a very low pulsatility of flow, and the PI is detected or calculated from the pulsatility of flow. That maybe causes this erratic behavior, and my idea is that the PI detection algorithm derived from the HeartMate 2 cannot be applied to the construction of the HeartMate 3. With the HeartMate 2, a low PI would mean good unloading due to high flow. It's the same with the HeartMate 3, but with a high PI in the HeartMate 2 would mean poor unloading with LV contractibility. But in the HeartMate 3, this can, due to the low flow caused by hypovolemia, leading to suction. That means high PI, also maybe suction. Now, the design of the pump improves the behavior for pump thrombosis or against pump thrombosis a lot, but still there is the risk of pump thrombosis. Two possible scenarios. We can get an occlusion by an ingested thrombus into the trumpet-like inflow. If this thrombus is bigger than 1/4 of an inch and solid, that would lead to a total occlusion and a persisting low flow situation. The second scenario would be if there is some small thrombus passing the pump. It would characteristics changes of the maglev signals. We know that this happens from our experience of the other magnetically levitated pumps like the Incor or the Durahard. I will go into the details later on. So, to the first scenario, occluding inflow thrombus, there would be an abrupt and persistent low flow, low power, low PI situation. Unfortunately, we have no curves available for the clinical user, so this situation can be detected only vaguely or only from the clinical signs. Of course, there is a lot of data stored in the device which we can download. I will have some words about that later on. Let's first just look to the data. On the right side, we see the abrupt dropping of flow, PI, and power consumption. And if we zoom in, that means if you look to the, not the periodic, oh, there is a misspelling, periodic log, but to the event log, we can see this drop persistent and a lot of data stored after this drop. That means there is a constant alarm situation. So let's see. The second scenario, you see, if I touch the spinning rotor, everything would be same, stable. So a thrombus passing the pump may deflect the rotor without impairing the rotation of the impeller. But the readjustment of the correct position of the rotor will cause altered or higher magnetic levitation signals and currents. You can imagine that a deflection of the rotor has to be pulled back into the center by higher magnetic forces. That means something is happening internally, and if we look close to the recordings, we can determine if or what has happened. So if we have a transient, like a low flow situation, on the right side, the blue line, and a high power situation caused by a strong magnetic levitated field necessary to stable the unbalanced rotor, we can deduct thrombus passing the system. How can this be explained? We have two values stored in the device log. The rotor displacement is one. If you look to the pump sketch, a high pressure and a low pressure localization inside the pump will move the rotor a little bit eccentrically. So the rotor displacement is an important value and is measured constantly. If this rotor displacement is changing transiently, this may be caused by a passing thrombus. Also, there is a connection between the rotor displacement, the red curve, and the pressure head. The pressure head is not displayed here, but it can be deducted from the flow. If we have a high flow situation, the pressure head must be low. If the flow is low, the pressure head is high. And you see that a low flow, high pressure head means a large displacement of the rotor. So the rotor displacement value it can be very interesting if you want to have information about the pressure created by the pump. Well, let's go back. And if a thrombus is passing the impeller, the hydrodynamic properties of this impeller are changed, altered, or worsened. That means that a thrombus sticking to the impeller will cause a lower pressure build-up, possible build-up of the rotor. So a low displacement may lead to the information that there was a thrombus passing the pump. Also, if we have a thrombus sticking to the impeller, there is an imbalanced rotor, and that causes a vibration of the rotor, like your car tire if it's not balanced. And there is a second type of value stored in the log files. It's a rotor called rotor noise. This is something displaying the ability of the vibration of the rotor. Again, we have some data from a patient, a passing thrombotic particle, and now we are looking to the levitation signals, It's just a very short transient in the log file, but if you look in the event file and zoom into this information, we can see that the flow is dropping. That means the pressure increased by the impeller is lower because of the changed properties or hydrodynamic properties of the device. And also, we see this maglev rotor noise value going high up into the 160 microns, and after passing of the thrombus back to normal. So this is a very good or impressive data set for passing thrombus particles. In addition, with the patient, we took this data from, we had some neurologic events later on, directly after this event, which tells us, well, there must have been some thrombus passing the pump. Now, how do we get to this pump? That means data conversion and display, which is not possible from the company. If we download the data and send it to SJM, we will get a nice report which tells us, well, nothing. 40 days of data, current set speed, we know. The average power range from 3.7 to 4.3 watts. Well, this is not really interesting, and also we can read this on the clinical monitor as well. Calculated average flow, of course, and well, there were no unusual events seen within the log file. That may be, but we would like to have some more information, like we do have in the clinical monitor of the HWAT system. So there's a binary data downloaded from the clinical monitor, and of course you cannot find in the data direct values of what was measured. But on the other hand, it's not really difficult if you're a computer buff to find where the data is located into these huge numbers, log file numbers. Where, as you probably know, there are 4 types of data downloaded from the monitor. It's controller event file, the controller periodic log file. There is the information about speed, flow, PI, supply, voltage, alarms, anything that is directly telling us about the patient. And there is the LVAT internal heart made 3 event file, the L3E and L3P, which tell us more technical stuff about the magnetic levitation and some other internal data, which also is interesting if we have the suspicion of a thrombotic particle passing the pump. So I won't tell you how to in detail derive this data. My dedication is just to show that it's possible, and thus it's possible for everyone to get this information, and thus my idea is that the company or the manufacturer should provide the VAD coordinators with some tool to do this. Because even if we don't have a fatal incident like a neurologic event because of a passing thrombus, there is also very interesting information about the behavior of the patient. What information can be derived from the periodic log file of this patient? Let's see to the patient's course. In the beginning, the patient was on ICU. And we have higher sampling rate. As you can see in the curves, they are more detailed. The patient went to ward. There was a different volume management, probably. The unloading of the left ventricle was better. Flow was higher. PI was lower. The patient went to rehab. And now suddenly we have some spikes in the PI, probably suction events, because they are coming as transients from a very low PI to very high PI. We have the first outpatient visit of this patient directly from rehab, and there was some speed change, lower speed, because of these high PI events. And after it's a 5 days interval on the x-axis, After another week, a second visit, and we could see some changes again, lower flow, more smoothly increasing PI, and that led us to the finding that the medication, cardiac medication of the patient probably was not correctly set. We suspected higher blood pressure, and this was also correct. And well, the rest of the curve is missing. They adapted the clinical, the cardiac medication, and everything went to normal. But all this information would be missed if we don't have some curves, if we just have to rely on the numbers displayed on the monitor. Also, the event file logs, there's some more information. For one is on the left side, we have some repeated events, PI events, as you can see with the black curve, the changing of the speed. And also we get some information from the cable voltage about the behavior of the patient. You see all these transients to the low. This always is exchange of the power of the batteries to the AC power or vice versa. And what is also told by this picture is that there are no events, because the entries, the data in the event file is only put into the file when there were battery exchanges, no other issues. Of course, the time axis is a problem here, because it's not a regular time axis. Now, there's additional information if we are able with our log file viewer tool, if you can superimpose the event files to the log files, as I have done here with my tool. Especially on the right side, where we see the increase of the PI, as you have seen before. If you look to the event files, these are not average values. We see that we already have quite high PI values stored, not at the 1 hour intervals of the periodic log, but in between, just by chance. So the increase of the PI during the time caused by hypertonus of the patient is still more impressive if we put both information together. So, well, this is my tool. It's Excel macro based, so not really scientific, but working quite well. Conclusions. In stable working conditions, the black box system HeartMate-3 is sufficient. But to set the optimal speed and to investigate unstable situations, pulsatility has to be evaluated, but the PI index offers no sufficient information because the calculation algorithm seems not to be appropriate, and there is no real discrimination between contraction and suction spikes. For routine checks and emergency situations, I think the selection of numerical data on a screen is poor and outdated, and a clinical tool to produce the trend curves from downloaded data of the HeartMate-3 could and should be available. And of course, the best way would be if it's available from the company. So let's put some light to the black box, and thank you for your attention.